Here we're going to combine two fundamental ideas that we've seen so far in analyzing or interpreting graphs of functions of two variables. We're going to combine our partial derivatives with contour diagrams. So this is a good question to self-test yourself with first. Let's imagine that we're at the point 1, 1, so we're here on the graph. What can we say, or what can we infer about the partial derivative of h with respect to x and h with respect to y at that point, knowing that we're taking the usual flat axes of x increasing to the right and y increasing to the up direction, in the up direction. We'll give you about 5 seconds here. You can pause if you like, and then we'll take a look at how we could go through that analysis. But take a good guess first. Okay. Remember how this all gets derived. When we're looking at the partial derivative of a function with respect to its input, we always ask the question, what would happen if the variable we're differentiating with respect to was increased? In other words, what if we took a super small step from the point we're at to a point to the right, if that's the direction of positive or increasing x? Well, it's pretty clear from the contour diagram that we'd be going from a contour at height 60 towards a contour of height 50, and that would be going down. So this would be a higher place, and then we're heading towards a lower place. And that means that when x is increasing, h is decreasing. We're changing contour lines and going down. What we expect to see there is that the partial derivative, h with respect to x, will be negative. In exactly the same way, if we were to take a step in the positive y direction, so if y were to increase from our current point, then we would see that h is going to increase because we're moving from a contour with height 60 towards a contour with height 70. The peak of the hill's up here. We'd be working, at least loosely, towards that. But most importantly, the small step that we take, remember, small delta x, or small delta y, that small step is going to take us up and towards a higher contour, so we expect the derivative to be positive there. Now what about the point B? Let's take a close look at it. The x derivative is actually pretty straightforward. If we increase x, we take a step to the right, again, same axes. The key thing though is to make a very, very small step, because we're on a contour right now of height 50, and if you take a huge step, we can obviously go down again. But if you imagine yourself sitting at this point on the graph, on the surface here, if you took a small step, you would be heading towards the next point, the next crossing, which would be at height 60. So you'd actually be going up a little bit, maybe up a bit further, and then back down again afterwards. So in a small step, so a small increase in x would give us an increase in h. And so the partial derivative there would be positive. Last but not least, what if we looked at the h derivative with respect to y? So we're at this point, and this is where it really helps to zoom in. Again, this is a small or even a tiny increase in y. Increase in y. If we take a very careful look around this point here, what we would see is a contour line, and again, we do this more rigorously if we had formulas, but if we had that point and we took a step in the y direction, the step keeps us on the contour. And that is a distinctive outcome, something we haven't seen yet in these examples. If we take a step and stay on the contour, well then what's our change in h? Well, if we're on the same contour, this contour is all at height 50, if I take a step and I stay at 50, there's going to be zero change in h, and so the derivative, the partial derivative of h with respect to y is going to be 0. And that's going to be true in general. If a step stays on the contour, then your change in the height of the function is going to be 0, and so the partial derivative in this case here, will equal 0 as well. So that's going to be a special case. Almost any other point we pick, let's say we picked a point here, positive, if we went in positive y, we'd be going towards the 50 contour, so we'd be going up. If we went to the right, we'd be going down. It's easy to analyze those. It would be any place where the step is exactly in the direction, let's say here as well. If the contour was tangent to the x step or to the y step, that's where we're going to get this kind of zero derivative happening. Last but not least, we can ask when the slopes are steep, and here we're going to be very specific about the slope in the positive x direction. Again, an increase in x corresponds to this partial derivative here. So if we want to pick a point on the contour where the x derivative seems particularly large, that's one where the slope in the positive x direction is particularly steep, or steepest. And that, remember, means that the contours are closest together. When we look at our diagram, this is a relatively flat region because it takes a while in terms of xy distance to get from 20 to 30. Whereas in this region over here, if I take the same size step I took over here, I can cross several contour lines and get a much more dramatic increase in my height, which is represented by each contour here. I can cross more contours. And so this region here, let's call it region R here, in the region R, the x derivatives, x partial derivatives of h are large. Again, finding the largest might be a bit tough. They're certainly pretty close to as large on this side, though they would be negative. But if we're looking for steep slopes, we look for tightly packed contours, and because we're looking for steepness only in one direction, in the positive x direction, then we'd want the contours to be really, really close when we move left to right, and this kind of region here. It wouldn't be true down in this region here because it'd take me a long time to cross contours if we move left to right. And so that lets us combine, again, our study or our representation of two variable functions as contour diagrams, and then overlay that with our understanding about partial derivatives that we've also developed.